Okay, so last time we ended up writing down this equation given our solution, our wave solution. So now let's imagine going the other way around. Let's find that solution given that equation. Where do we end up? Well, it's not surprising that we'll end up with something that we're familiar with, but it's not the complete solution. So that follows from there, and when we integrate, right, we're going through the logarithm and we end up with psi being some function that's a constant in time, so that could be some c of r, some function of space, and that of course is the e to the I k r part, which we can't recover from this, but we do recover e over I h bar, e over I h bar t, or let's write that in a more familiar way with a minus sign at the top. It looks like that. So we can recover the time part, but not the spatial part. So we don't have a complete differential equation that will get us our solution. So we're missing this e to the I k r part, and with a little bit of thinking we can recognize that that will come from spatial derivatives, right? We want spatial derivatives to bring down the wave number part of this, and the wave number part of this is related to the E part, right? We know that this number, the energy, is kinetic plus potential. And so if we're just thinking of a particle that is not acted on by any forces, there's no potential part. There's just a kinetic term, and through P equals h bar times k, we can relate this quantity. We want to pull down something like this and relate it to E, and then we'll be able to get a full differential equation. So what does that look like? Well, it turns out that we need to pull down two factors of k, because we need to construct a k squared, because we have a p squared in here. So through this, we see that we need a k squared. We need two factors of k. So we're going to take two spatial derivatives. That brings in the del squared of psi, which we can write out fully as, right, for an x, y, z coordinates, then that looks like this. And that ends up getting us, we have a minus sign, that gives us the kx squared and that multiplies psi itself. So again, so P is equal to h bar k, and E is equal to p squared over 2m, and then it follows that E is also h bar squared times k squared over 2m. And so k squared, right, k squared is 2me over h bar squared. And so this equation ends up So we have del squared psi is equal to let's see, in terms of the energy, this becomes minus, right, k squared is 2 me over h bar squared psi. And so we can say that minus h bar squared over 2m del squared psi is equal to E times psi. Okay, so we are in a situation where we have E times psi, just like we did when we considered the time part. And so the two left-hand sides, this and this, right, have to be equal to each other. And that means that we have uncovered the following relationship. Okay, so this part, this is a spatial operator. Usually it's written like that, right? The Hamiltonian operator. We're not specifying coordinates there, but then we've just shown that we can write the full differential equation that gets us our solution as that. And this is actually more general than this equation, because this equation only has a kinetic part, right? A p squared over 2m part. We can generalize the H operator to a kinetic plus a potential part, and the equation looks like this. So this is our full equation. It's called the time dependent Schrodinger equation.